Hey everyone, welcome back. Now today's debate happened on modern day debate between TJump and Flat Earth Aussie Jesus, also known as Iron Horse. Kind of funny because the host does refer to him sometimes as Iron Horse and sometimes just as Aussie. But that doesn't change the fact that he does not understand anything as far as physics. And as a lot of other flat earthers, thinks that his experience trumps all of the science that we know in all of the books that are in the schools that help us learn the truth about how things actually work, not just from observation. I think this is how it works, but actually go in depth, study, and figure out the exact cause of what's happening. So TJump does a fantastic job, as usual, trying to convince him and break down some examples to very small, very easy concepts to which Flat Earth Aussie Jesus just, I don't know. He looks like Jesus, I guess, with the beard, and his thought
Flat
is
Earth
just
truth
like
and
back then,
realization
2,000
has
years
dominated
ago,
my existence,
when
after
supposedly
formerly being
Jesus
interested in all manner of hidden
walked the
truths
earth.
about our reality.
So with that, I'm
Being
going to leave
interested
you
in
so
all
you guys
manner of
can
hidden...
enjoy the
finish
rest
that.
of the debate.
Today I intend to
I'll see you
destroy
guys
the
next
ridiculous
time.
notion that mass attracts mass and liquids and gas by virtue of being massive, contained by the non-solid barrier of absolutely nothing. Does gravity exist? So far as the scientific consensus of things of mass dropping through the medium of air at 9.8 meters per second squared, absolutely. That's the observable consensus of physics everywhere on the planet Earth. The question is, why does the ground stop things dropping? The answer is resistance. Resistance from what? The density of the ground. So far, density is already winning over gravity. So 1 point to resistance as the fourth, 0 to gravity. Well, why doesn't it fall up, asks every incredulous glober ever. Well, what sort of resistance does the density of air give? Well, at free fall speed, it offers very little resistance, most of which can be explained solely by the attributes of shape alone, though relative density is definitely a real influencing factor as well. The idea that everything of mass is pulled towards the center is the height of pseudoscientific belief. Unnecessary, unrequired, absolutely extraneous to the reality of the stationary planar Earth we clearly live upon. I challenge my space-brained opponent to find just one example of everyday life experiences taken from space, showing ships or planes from a distance, seeming to appear to operate upside down or sideways on the spinning space ball, or even any object dropping in a direction apart from the universally observed direction of down. Even the most simple experiments can dismiss any motion of the Earth, which is just as important a factor of the heliocentric dialect as the equally mythical gravity. We drop a rubber ball onto a moving conveyor belt, the momentum of even a slow-moving belt will impart some momentum onto the bouncy ball, and it will rebound in the direction of the momentum, no matter how tiny the speed. Yet, drop it directly onto the floor, it drops straight down, it bounces straight up. According to our heliocentric faithful followers, the ground isn't just moving eastwards at over 1,000 miles per hour, but has another velocity on its annual journey around the sun, the equivalent of almost 87 times the speed of sound. I can give multiple examples how relative density is basically the only relevant requirement now that we've analysed and dismissed all that is absurd about previously believed earthly phenomena. But both the solid balls with no air content drop 9.8 meters per second squared in the medium of air, as they both possess the same air resistance. But now, in water, gravity gets selective. Why? It pulls the lead ball down to the solid bed of the water, but leaves the rubber ball floating on the surface. This is a prime example of relative density and buoyancy. While it might be reasonable to say that the word weight can be substituted in many instances where the word gravity is used, even that would be a gross oversimplification. Gravity is not only an outdated theory for an outdated mythical belief, but we can equally dismiss it as the ancient superstitious explanation for tides. It may have served its purpose very well as the go-to god of the gaps throughout our former, somewhat darker ages. Yet the explanation of how the one mass of only one moon can pull water by virtue of its own mass twice per day has to be on par as ridiculous as a pressurized atmosphere bounded by a vacuum, like a helium balloon stuck to the ceiling with no balloon.
TJump, the floor is all yours.
Gravity's really easy to prove. All we do is take a container, suck out all the air, make it a vacuum, put an object in it, and for some reason, even though there's nothing in there to cause relative density, it's completely empty, it's a vacuum, it will still fall down. And if you turn the container upside down and put a ball in it, it'll still fall down, which means there has to be some force that isn't relative density that is causing objects to go down and not up. Because if we have a vacuum, there's no relative density, but it's still going down for some reason. That disproves relative density and disproves all of Flat Earth Aussie's argument and shows that there must be some force that pull things through a vacuum, and we're going to call that gravity, and it works. Everything else he said is scientifically wrong. The moon does pull water in one direction. If you pull water in one direction in a tub, the water on the other side will come to fill the giant hole that's placed, and that creates a second wave. There you go. That's where you have double different tides, different times of the day. Because if there's an absence of water, the rest of the water is going to rush to fill the absence. There you go. Two tides, pretty easy. Yeah, it's not hard to prove that at all. There's also like the Atvos effect. If you are traveling east, you are actually lighter than if you're traveling west because of these effects. So it's not like this is hard stuff. I don't know what Aussie's confused about. Gravity's proven by vacuums and dropping balls in them. Problem solved. I'll conclude there.
What do we observe in nature is things drop unless they've got something of density beneath them to resist them. There's no evidence of anything falling sideways towards something due to its mass. It all goes universally straight down. That's physics. First law of it, observation.
Yeah, so if there's zero forces, there is zero movement. So any movement requires a force. So if it's going down, that means there has to be a force causing it to go down. Otherwise, it would do nothing. If there's no forces, it would do nothing. It would just stay there and do nothing. So there has to be a force causing things to go down, right?
Well, actually, there's a force causing things to stop falling, and that is density.
Where does the force coming from? When I let it go, something has to add force to it to make it go down. What is the thing adding force to it to make it go down?
No, you are creating a resistant force with your hand, and you're removing a resistant force. You're not adding another force, you're removing
the resistance
one.
is irrelevant here. I don't care about the resistance. Why does it continue to speed up when I let it go? It goes faster and why does it go faster? If it has to change. It goes from 0 to plus 1 meter per second, 2 meters per second, 3 meters per second. It's speeding up. It's going faster. How is it going faster? What is adding speed to it?
By virtue of its own mass and the lack of resistance of the medium of air.
You can't just say it automatically adds a force to itself. It can't do that because it could add, if it was only itself, then it would go in no direction. So the reason it's going in one direction, not the other direction, there has to be something there to add a force to the thing to make it go in one direction, not the other direction. The thing itself can't do that. What force is causing it to go down?
Okay. Is it still going down now? No, because it's met a place of resistance. You applied a force to it by lifting it. You applied another force of resistance by holding it, then you remove the resistant force. So physics, because it's a thing of mass, is automatically going to want to drop until it is at a place of resistance. It is not still dropping, is it?
Wrong, Aussie. No. It does not automatically want to drop. Something has to make it want to drop. It doesn't drop automatically, Aussie. There's no force inside of a cup that makes it want to drop, Aussie. It doesn't work that way. Mass doesn't automatically want to drop. Aussie, if this is an equal and opposite reaction, me holding this, that means there has to be something going up and something going down, Aussie. What is the thing going down, Aussie? What is the thing I'm resistance against,
its own weight. Weight,
Aussie.
It's heavier than air.
Its own weight doesn't cause it to go down, because if I put it in a space with no gravity, it'll just sit there. So why is it going down?
It's the relative density. If it was a helium balloon, would it go down? No, because it's not more dense than the air. It would go up. Such a simple concept. There's no point continuing to argue something if you're going to be that thick about it and you can't get it.
So why?
And there's no such thing as a vacuum. There's no such thing as a vacuum anyway.
Yes, there is. We can create vacuums all the time. So if we create a vacuum with no particles inside of it and put an object in it, it's not displacing anything. There's no relative density. There is zero density. And why does it still
But we can't create a vacuum. We can create close to a vacuum, but there'll always be some amount of density there.
Good enough. If the molecule's literally not touching the top and the bottom, that's zero density. So zero density, object in it, it falls. Why? Why does it fall? It's not displacing anything. Why does it fall?
It's displacing something.
No, it's not.
Something
that's what
that's
a vacuum means.
unable
Not
to resist
displacing.
it.
There's no displacement.
It's a near vacuum. You'll never get a total vacuum anyway.
I don't, Aussie, I don't need a total vacuum. I just need enough of a vacuum that it's not displacing anything. We can create vacuums that the particles are so far away that the object isn't displacing anything. So yes, we can create it where there's zero displacement. It's not displacing any particles at all. Still falls. Why does it still fall, Aussie?
Because it has mass, and mass requires resistance.
Mass is not a force.
So
mass doesn't go down. Mass is is not a force. So
but
why does mass go down? Why does mass
literally
go
what you're
down?
saying gravity is? Because that's where things of mass go. We live in a relative density realm. Everything of mass
Aussie, you can't just say
goes down. There's a universal down.
No,
it never falls sideways, does it? Not even in your vacuum.
Why does it go down?
Because there's nothing dense enough to resist it.
Aussie. No. You can't. You have to have a positive number here. So if I say, why does something going at a speed of 7 go at a speed of 7? I can't say because nothing is stopping it. Why does mass fall?
No, that's right. The Newton's law says for every action, there's an equal and opposite reaction. So if you don't perform a force in the first place, like picking it up, then it won't drop. If you pick it up and you leave it somewhere where there's nothing to resist it, it drops. It's really, really straightforward stuff. You don't need extraneous forces to describe it. It is just the reaction to the initial force that you placed upon it.
Yes, it's an initial force called gravity. That's why it goes down. You don't get an option there. If it goes down, that's a force. If it moves, that's a force. If there's no movement, then there's no force. So if you're saying it's moving, you're admitting there's a force.
Throw something up in the air.
No, wrong force, Aussie. If something goes down, if anything is going down at all, if anything is ever being pulled down for any reason, that's a force, Aussie. You lose. I already debunked your nonsense there, Aussie. If an object is moving, that's a force. There has to be a force to cause the movement. So if an object is falling for any reason ever, there is a force causing the falling. Resistance doesn't cause the falling, Aussie.
No, throwing it up in the air in the first place did.
No.
It's just a reaction. It's just a natural reaction to applying a force. If you left it alone in the first place, if you didn't apply a force, it's not going to drop, is it?
Wrong, Aussie. If I throw an object up, I'm applying a force upwards. There has to be something else to cause it to come down. A different force. Another force, Aussie. Basic logic. It can't move anything if it's equally dense on both sides. If you have something equally dense on both sides, it will not move. That's how density works. You understand how density works, right?
Does your vacuum chamber have dense walls? Does your vacuum chamber have dense walls? Does it have a floor and a ceiling?
Density. The walls are not a gas. They don't apply any
walls
force.
And floors exist.
Walls and floors exist. If walls and floors don't apply a force to an object in them, that's what the point of a vacuum is. If the walls applied the forces in a vacuum, it wouldn't be a vacuum, Aussie. It'd be filled with walls. That's not how a vacuum works, Aussie.
So the universe without walls, being a giant vacuum, how do we have an atmosphere on Earth?
Gravity and electromagnetism, the forces that pull things together. Yes.
So gravity is electromagnetism now, and it pulls on air.
Gravity does pull on air. Yes. Electromagnetism also pulls on air.
So why is the air up? Why is the air up then? Why isn't it all on the ground? Well, how come I can get a straw, stick it in a glass of water, put my finger over the top, and lift the straw up out of the water, and the water doesn't fall back down? A tiny little vacuum closest to the center of gravity can beat gravity. A tiny little vacuum force.
Because of the strong electromagnetic force.
That's strong enough to pull all the air up to that.
That's because of the strong electromagnetic force. It's 40 orders of magnitude stronger than gravity. This is very easy, basic stuff, Aussie.
Okay, so if I get a vacuum hose and I start drawing some water out, I can lift it up over the roof of a building. And as long as I put the other end lower than the water source on the other side of the building, that water is going to flow all the way up the hose and come out the other side. That's another example of a vacuum force being way, way stronger than gravity, which has no say in the matter. That water will forcefully flow out until it's all lower than the outer end. How do you explain gravity?
You can jump, Aussie. Like, it's easier. You can just jump up and down. You can use the strong and weak electromagnetic force to tension your muscles and then go up above, fight gravity. So gravity is 40 orders of magnitude weaker than the strong and weak electromagnetic force. So obviously you can use those to overcome gravity. That's why rockets work. Gravity can still pull things in from long distances.
But an air molecule has virtually zero mass. Like, yeah, it's like probably 0.00001 grams of mass, if that, even less. So
That's
if
no
gravity is
mass.
a force of attraction, an electromagnetic attraction to something that's virtually non-existent, then how the heck can we be hurtling through a vacuum of space and still have an atmosphere?
Because vacuums don't apply forces, so vacuums wouldn't push anything away. So when you like put your finger on a straw and hold up water, the vacuum is doing nothing. There is no vacuum force. It is the air around the straw that is pushing the water. There is no vacuum force. So if space is a vacuum, it applies zero force. Okay,
I think I've demonstrated that a vacuum force of a simple siphon is way, way stronger than gravity. And that's just a very simple vacuum force. It's a very tiny one. So
there's no such
to
thing.
say that the universal vacuum is weaker than a hose, that's the most insane thing ever.
Again, Aussie, there's no such thing as a vacuum force. There is the force of other particles pushing. So if you create a vacuum on one side of a straw, the vacuum does nothing. The vacuum is not a force. The other particles are pushing the water from the other side.
Like I said, if you got the helium balloon stuck to the ceiling without the balloon, it makes no sense. But we've got the whole atmosphere stuck to the ceiling of the sky without a balloon. It makes no sense. We can't have it. You can't have a pressurized atmosphere in a vacuum.
So you've debunked your own silly position, Aussie. So if a vacuum force is a thing, why doesn't the water fall? So like you have a straw and you have like your finger on the straw and there's water in it. Why doesn't it fall? Why doesn't the water fall out of the straw when you hold it up?
We might have to do this another day. I'm not even getting anything from you here, sorry. I live in a pretty poor reception area here with internet, so.
Let's say you have a straw, it's full of water, and you're holding it up with your finger. Now, if stuff automatically falls like you think it does, why doesn't the water fall out of the straw?
Because you've created a vacuum force to prevent it, haven't you? That's the power of a vacuum, and it's only a tiny little vacuum. The gravity has no say in it. So
the vacuum's on the top, right? The vacuum's on the top of the straw, right?
Well, it's at the top end, yeah.
And what's on the bottom end?
Yeah, your water.
Yes, and the air below the water, right?
Well, yes.
Okay, so why is the water not falling through the air?
Because gravity doesn't exist. It's a myth. You've got a vacuum force holding it up.
It doesn't matter if gravity exists. Something has to stop it from falling. Why is it not falling? Something has to like hold it up from the bottom.
The vacuum held by your finger. As soon as you release that vacuum force, it does drop, doesn't it? So there's no gravity involved. There's a vacuum force overriding any possible hope or thought of any amount of gravity whatsoever.
So
it
the vacuum
shows that
at
the vacuum is a force.
So the vacuum at the top of the straw is touching the water at the bottom of the straw?
It's what's holding it in, because the water itself, being a fluid, has no air passing through it, and so it creates its own vacuum force itself. That's one of the properties of fluids.
What? That makes absolutely no sense. Yes, so if there's a vacuum and then water and then air, the air is...
Because you've created a vacuum seal inside the top of the straw that the water's own weight pulling against that creates enough of a suction to prevent it falling any further, which is why if you release your finger, it falls back out because of the relative density. So it just shows that that tiny little vacuum force can override gravity just in front of your face, that you can do it in the bloody cafe or at your kitchen table or whatever. It's something that anybody can prove to show that gravity is non-existent. It's not needed to explain the observations of pressure gradients, vacuum forces, and fluid dynamics. I just said you've made a tiny little vacuum force which overrides any concept of gravity because of water's own density.
What? Bro, what are you talking about, man?
How can you possibly have the moon overriding Earth's gravity when it's a sixth of Earth's gravity and creating a secondary high tide on the rear side? It's just physically impossible if you apply just the simplest bit of logic to it. There's no way you can use gravity to explain tides at all.
No, it's pretty simple. So like if you have a like say a bathtub and you put your hand in the middle of the bathtub and then you push your hand, you're going to have a big ball of water here and a big trough of water here, right?
Yeah.
And then the big trough is going to be filled by the water over here. This water is going to like fill the trough, right?
Actually, no. Fluid dynamics makes the whole wave go and hit this back end of the bath, and then when it flows back, it will fill that trough. It's not going to fill that trough with another wave. You're going to create one wave with your hand, not a second wave to fill the trough. The water will rebound off the side of the bathtub.
So the water behind your hand will just stay there. It won't fill the giant hole you've created. The hole's just going to remain there, and the water isn't going to fall into the hole until the first wave hits the edge.
Back. It will bounce back from the other edge. It'll slosh backwards and forwards, and that's a tiny example just in a bathtub. We're talking about oceans.
So yeah, let's say we're in the ocean. If I'm in the ocean and I put my hand in the ocean and I make a wave, you're saying the big hole that I just made will never be filled until the wave hits the other side of the Atlantic and comes back?
It's no comparison.
If you make a displacement. So if I put my hand in water and I push the water, there's going to be a wave in the front where the water has been moved, and there's going to be a wave in the back to fill the first wave, right?
Not necessarily a wave, just water naturally finding its level. And there's no way that you can
tide, Aussie. If you want to call it water finding its level, that's the second tide. That's how it works. Okay. Congratulations.
Tell me then how the moon is anything like a hand pushing through water. You're saying that the gravity is pulling water.
Yes. So it's a big thing that pulls the water in one direction, like my hand pushes the water in one direction. It's a force.
Well, that would create the second tide right behind it, wouldn't it? That'd create just one wave and another wave, and you got your two tides in 5 minutes. But you don't have two tides in 5 minutes. You have them 12 and a half hours apart.
Right. So the size of the wave is determined by the amount of water you move. The more water you move, the longer it takes for the water to fill the hole, right?
Tides don't move in one single wave. They gradually rise over a period of 6 hours, and they gradually go down over a period of another 6 hours, and then they go back up again over another 6 hours. There's no such thing as a tidal wave creating the tides in one big burst and then having a low tide in between as the next wave comes and hits.
Imagine the ultimate big sky daddy puts his hand in all of the waters on the earth and just moves all of the waters. How long would it take the water to naturally flow to fill in the first half that the God moved the waters?
5 minutes, if that. 2 minutes.
Okay, so
your sky daddy that you're talking about, is bigger than the moon.
Yes, so ultimate sky daddy, super God decides to put his hand in the middle of the earth and move half of the water to like one edge. And we want to know how fast the water on the other side is going to fill the hole the sky daddy's hand left. And you think it's going to cover the entire half of the earth in 5 minutes?
Yeah, I think it's going to actually flood the entire world in 5 minutes.
Let's talk about reality, like in what's actually there. What's a tsunami? What is a tsunami?
A tsunami is generally a wave created by an earthquake underwater and displaces a large volume of water very quickly.
Let's say we have a tsunami instead of a giant hand because you want real things. So a tsunami moves a large portion of the water. Does the water automatically get refilled in 5 minutes?
It creates a massive flood depending on where it hits.
Yes,
and then slowly
behind the tsunami, does it take 5 minutes for the rest of the world's ocean to fill the giant hole the tsunami has left?
No, because the same water goes back and fills back where it came from, like it does in the bathtub.
Right. It takes longer. It doesn't work like that. You create a giant hole in the ocean because the tsunami pulls the water out of the ocean. It takes quite a long time for the water to move and fill that because water doesn't go at the speed of light like you think it does. It actually takes some time because of how physics works for the water to actually spread.
That's got nothing to do with tides, though, does it?
Yes,
that's got a physical effect of something happening to displace a large amount of water very quickly. And then that water receding is nothing like a tide. But it's still going to flow back the way it came. It's not going to be filled in by another wave coming, because if it kept on going, we wouldn't have land masses. Land masses are measurably above sea level, and that's what stops everything from getting flooded all the time. If you were looking at it on your globe, then everywhere is below the curvature of this massive mountain of ocean in the middle of 2 continents, and so they'd be below sea level.
Excuse me, the fuck did you just say?
It's just simple, observable logics. You have to bring in gravity to make the impossible possible. And that's why the globe is such a ridiculous concept, because without it, we can explain everything in physics without gravity. You've got no idea what you're talking about. We're talking about a 6.25 hour difference between the first high tide and the second high tide. How can a wave coming a minute or 30 seconds afterwards possibly be an explanation for tides? That's ridiculous.
Do bigger waves move slower, Aussie?
What's that?
Bigger wave.
Bigger waves move slower.
If the wave is bigger, does it create a larger wavelength between the next wave?
I guess you could say so, yeah.
So if you have a really, really big wave, then you're going to have a really, really big trough, and it's going to take a longer time to fill the trough, isn't it, Aussie?
But it's not going to take a quarter of a day. That's just not how it works. It's not going to create a low tide immediately for the next 6 hours.
If the bigger the wave, the longer the trough. If the bigger the wave, the longer the trough. If you get a big enough wave, yes, you'll get a 6-hour trough. Congratulations. It's just basic physics.
You're insane, mate, if that's what you think. You're absolutely insane. You've got no ocean experience whatsoever. You've probably never ridden a surfboard in your life. You've got no idea how waves work, no idea how tides work. I've spent years of my life, decades, observing tides. I've watched a high tide creeping up across dry sand as the moon is far into the east, still approaching.
So you may have spent years watching the waves. I have spent years watching flat earthers and debaters who don't understand anything on debates. And I can tell, and based on your logic, I should understand more about flat earthers than anybody, because I've spent years watching them talk. Clearly, that's not the case. You spending years watching waves is like me spending years watching flat earthers. It's still a mystery. Everyone who's older than 24 has decades of experience in reality. That's just basic logic. And obviously, it's a natural phenomenon in nature. Clearly, that's the case. Flurfs are also a natural phenomenon. There's nothing supernatural about them. Literally nothing you said makes sense.
Comment, I believe, from Crawdaddy that we missed. Iron Horse. Find a playground, get on the merry-go-round, and do one spin over the course of 24 hours and tell me how thrilling the ride is.
Yeah, well, that's a lovely example of people that live in a world of ignorance. Because if we're going to make this merry-go-round even close to resembling reality, we've got to have it with a radius from the center to the outside horse that you're riding on of 4,000 miles. And you've also got to have it sitting on the back of a truck, for example, or something, a supersonic jet, where this jet is flying through across the ground at about 66,600 miles per hour. Now, I can assure you that even without being on the back of a truck, if it's just moving once per day at the end of a 4,000-mile radius, you are going 1.35 times the speed of sound, and you'd better hope you're wearing your Superman cape and a good hard hat.
Gotcha.
Angular velocity is the same no matter what distance you're going at, so it doesn't change if you're like a foot away from the center or 1,000 miles away from the center. The angular velocity is the same.
Put a clock in the middle of a paddock and take the clock face off it and put a length of wire across to the hour hand and start extending that wire out just for 1 kilometre and see how fast you have to run to keep up with the clock. It's a ridiculous example to say that revolutions per minute are anything to do with angular velocity.
If the air is moving with you, you don't have to move at all. Everything will be moving with you, so you won't have to do anything.
But you've got to move with the hour hand. You know, we're talking 4,000 miles long. Can you even grasp the concept of something 4,000 miles long?
If
can't even grasp something 1 mile long when it comes to a piece of wire.
If the ground and air are moving with you, you could just hold the hand and you won't have to move at all. You will feel nothing. You'll just stand there.